Okay. Right. As we have discussed in instrumentation, already we discussed about mobile phase reservoir. That's simply nothing but it is a solvent container. Solvent container. There will be bottle in which you are keeping the required solvent. But when you are switching on the instrument, you need to keep enough volume of the solvent in the reservoir. Throughout the run, how much volume is needed? The volume you need to keep in the reservoir must be more than that. It must be more than that. That means sufficient enough solvent must be kept in the solvent reservoir. It is a bottle. Okay. Pumping system. Low to moderate pressure pumps. Because here in this case there is a pumping of the solvent. That's why here it is this one GFC is nothing but HPLC. It is liquid chromatography, isn't it? It is liquid chromatography. And the performance of the technique is improved by pumping system. This is nothing but HPLC. HPLC is not a single technique. In the beginning, in the first chapter, I told you classification. Under classification, I told you in HPLC we have different varieties. Okay? LSC, liquid solid chromatography. LLC, liquid chromatography. Okay? Ion exchange chromatography. If you use ion exchange column. Ion exchange chromatography. If you use a gel containing column. Gel permeation or size exclusion chromatography. Okay? Are you getting it? Yes. So HPLC is not a single technique. It is not a single technique. We have LSC, LLC, we have ion exchange, we have gel permeation or gel filtration, size exclusion, and also we have affinity chromatography. But instrument remains the same. What we are doing is changing the column. If you are using HPLC for ion exchange, you need to use ion exchange column. If you want to use HPLC with which you want to separate the molecules of different size, then you prefer to use this gel filtration column. Okay? So it is not something different chromatography. It is nothing but HPLC, but the column what we are using is column with porous stationary phase in the form of beads. So, is it clear? Now pumping system completed. Low to moderate pressure pumps that deliver the mobile phase at constant and controlled flow rate is needed. Sample injector introduces small well-defined volume of sample solution into mobile phase stream to avoid band burning. In all the instrumental chromatographies, sample injection must be very short. For example, if you are doing manual injection, you take the sample in the injector. Injector is a syringe. It is a syringe. How the doctor will inject the medicine to our body? By using a needle. The same. We are having a syringe with a needle. That is also called micro syringe. By using micro syringe, take the sample into the micro syringe, and there is a silicone rubber septum. The specialty of silicone rubber septum is auto sealing. After injecting the needle and after removing the needle, it will be immediately closed. Inject and insert the needle inside the silicone rubber septum, and then you need to inject very quickly, so that all the sample will be entering into the sample injection system at the same time. It will avoid band burning. As we know very well, in the first chapter I told you, we need little band burning, maximum band separation. One of the parameter here is how the way how you are injecting sample to the instrument. Okay. GFC column packed with porous gel or zero gels. Porous gel or zero gel means both of them are porous, but zero gels are dry. It is dry and hard. Okay. Whereas hydrogels are soft and spherical shape. Okay. That act as stationary phase and provide size selective separation. Detector monitors eluting components and converts concentration changes into electrical signal. It is a common phenomenon for any instrumentation. The detector works on the same principle, measuring a particular property and converting that property into electrical signals. Take it. Check. You need to increase the angle of inflation. Yes, right. Angle. Fine. That is okay. Any detector will function in the same phenomena. What is the phenomena? Measuring a particular property. It may be refractive index. Okay? It may be refractive index. It may be absorbance. It may be electrolytic conductivity. Measuring a particular property and then converting the property into electrical signal. Are you getting it? So that's why the magnitude of that electrical signal depends on the number of molecules, which indicates the concentration. That is how it will detect. We have of course different detectors. In this case, similar to all other HPLC techniques, we are also having different detectors here for this technique. Data system records chromatograms and allows quantitative and qualitative analysis. Quantitative and qualitative analysis we can perform. So now we are coming to role of column and stationary phase. Now we are discussing one after another. Role of column and stationary phase. As I have told you in all chromatographic techniques, column is the heart of the instrument. Column is the heart of the instrument because the separation process takes place in the column. And the detector is very important for the sensitivity of the instrument. The sensitivity of the instrument depends on the sensitivity of the detector. Okay? So, column is the heart of GFC because separation occurs entirely within the porous stationary phase. It is packed with uniformly sized porous beads. These porous beads are made up of polystyrene diphenylbenzene zero gels or silica based gels. Pores have different size distribution, determining which molecules can enter and how long they are retained. Different size distribution. That's why bigger molecules may not enter, the smaller molecules will enter. No chemical interaction, no absorption, ion exchange or affinity binding between allied and stationary phase. I already told you this point before, right? Molecules travel through. I already told you this one also, where they are distributing. Interparticle spaces, outside the beads, mostly bigger ones, the large. Intraparticle pores inside the beads, mostly smaller ones. And they distribute between, you see inside the pore beads, it is with the stationary phase. Outside the pores, outside the beads means, it is in the mobile phase. That's why I told you, if A is present, there is an equilibrium distribution of A between stationary phase and mobile phase. And we can write a distribution constant for this equilibrium. KAV. Or distribution constant, average distribution constant. Okay? That means now concentration of A in stationary phase divided by concentration of A in mobile phase. This is a distribution constant. Distribution constants of different solutes are different. No two solutes present in the mixture. No two solutes present in the mixture will have same distribution constant. Did you get this point? No two components present in the mixture will have same distribution constant. It is like a fingerprint. Each and every component have its own individual distribution constant. That's why we are successful in achieving separation. We are able to separate the components present in the mixture successfully because no two components are having same distribution constant. Column performance depends on packing uniformity. That means when you are packing the stationary phase in the column, you need to pack uniformly without keeping any gaps. Okay? There should not be any gaps. Packing must be uniform. Uniform packing must be there. Particle size. Stationary phase particle size also must be uniform. The diameter of every spherical bead must be the same. Of course, these are all available in the market, and of course they are same. Of course, we are having directly the columns. We can buy the column directly, in which there are different types of stationary phases. Column length also important. Of course, column length depends on the instrument. Instrument manufacturer himself, he will decide the column length. You cannot do anything. According to column length, just you need to attach column, that's it. Columns are readily available, and column length is depending on instrument manufacturer. You need to just attach. That's it. Pore size matching to Young molecular size. This point is very important. It dictates the selection of the column. As I already told you, there are different stationary phases. Within the porous beads, we have different stationary phases. Okay? With different pore sizes. You need to choose a column in which the stationary phase is having the pore sizes. Those are matching with the size of the molecules present in the mixture. Okay? For example, you consider a situation. Your mixture is having all very big molecules. Very big. Okay? And your pore sizes are very small. That means no component present in the mixture will enter inside the pores. Okay? When no component entering inside the pores, that means you are giving a mixture to be separated as a sample, and then when it is coming out, again it is a mixture. Mixture entered into the column and output also mixture, because those are not separated. Because there is no matching between the pores of the stationary phase and the size of the molecules. Because all the molecules are having bigger size when compared to the pores of the stationary phase. Is it clear? That means no separation. No separation. Therefore, column selection, stationary phase selection is very important. Very important in this thing. You can see here, it is showing sample mixture injected here. Here there are different molecules. There are different molecules shown in different colors. Have you seen the colors? Red color, green color. I can see the red color ones are green. Next green. Next blue. There are three components in the mixture. Three components in the mixture represented by red, green, and blue. And we can see the size. Red is bigger, green is medium, blue is small. Sample mixture injected, size separation now starting place. Now red ones are moving faster than green ones are moving faster than blue. Now you see, this is the band, one band started coming out. When this one started coming out, you are getting a peak. This is chromatographic peak corresponding to the molecules which they are coming out, red ones. And then after some time green, okay, and after some time blue, okay. So this one red, green and blue. What is there on the x-axis? Retention time or elution volume? What is this one? Elution curve means we can say that it's we can say detector signal, and in some cases even that is molecular size. Gels in GFC. Requirement of gel materials. Those must be porous. Gel materials must be porous, chemically inert, because we don't need any interactions. Okay? Chemically inert. No, there should not be any chemical reactions between the molecules and stationary phase. Between the mobile phase and stationary phase. No, there should not be chemical reaction. No chemical reactions. Even in this case, no interactions. No interaction. That means chemically inert. Mechanically stable. That means those porous beads must be mechanically stable. Right? So these are the requirements of gel materials. Two main categories: hydrogels, xerogels. I already told you. Hydrogels are the beads which are swollen by absorbing water. That means there is water inside. There is water inside the pores of the gel particles. Okay? And xerogels means those are dry and they are hard. Hydrogels are soft. If you touch, you feel very soft. Xerogels are hard. Those are dry, hard. It will be looking like a glass beads, but they have pores. Okay. Xerogels are dry porous gel materials which retain pore structure after solvent removal. Used mainly in organic solvent GPC or SEC. Size exposure chromatography. Characterized by controlled pore size distribution, high surface area, mechanical rigidity, solvent compatibility, and minimal swelling compared to hydrogels. Because hydrogels are swollen. This one not swollen. Examples: cross-linked polystyrene. You can see here the beads look like this. Okay, porous beads looks like this. Cross-linked polystyrene dihydrogen, porous silica-based gels, methacrylate-based gels, hybrid organic inorganic gels. That means we are having different gels, and different gels also having different pore sizes. That's why the selection of the stationary phase also very important. You need to select the stationary phase in such a way that the pore size is matching with the size of the molecules present in the mixture, right? Right. Gel pore size and fractionation range. Each gel has a specific molecular weight working range. Okay. As I already told you, of course, molecular weight depends on molecular size. Bigger the size, bigger the molecular weight. It is common. Okay. So each gel has specific molecular weight working range. Narrow pore size, high resolution. Wide pore size, broad separation range. Importance of matching gels to analyte size is very, very important, which I already explained to you. Column packing and conditions. What column packing and conditions are needed? Already I told you some of the points here. Uniform packing, critical for resolution. Uniform packing critical for getting high resolution. Avoid channeling and voids. That means non-uniform packing must be avoided. Column equilibration. See, for example, you pack. If you pack, for example, if you are doing manual packing. If you pour all the material at once, okay, and then the packing will not be uniform. Because you poured all the material at once. That means it will leave some gaps in between. Okay, it will leave some gaps in between. Then what you need to do? You need to take a little stationary phase and fill. Then adjust. Okay. If you need, you can say like this, so that it will settle tightly. Okay. Take again little quantity and again. So column packing should not be continuous. Of course, you are going to do some practical in the next year, next week, maybe the next week class. Because Prof.Vegi is here. Okay. He told me that next week he will conduct some practical for you. Next week. Yesterday he is here, but he told me to continue with what he has given to me until the content, whatever he gave to me, I am going to cover. So next week onwards, Prof.Vegi will take over. Right? Yes. So mostly he will contact you to arrange a practical session. In the practical session, there will be column packing. It may not be GFC column packing, maybe another column packing. If you know other column packing, it will be the same applicable also here for this one. Okay? So you need to take little and then try to pack it uniformly. Right? Column equilibration with mobile phase. That means after column packing, you need to pass the solvent, mobile phase, so that there will be equilibration with the mobile phase. Flow rate optimization. You need to also optimize the flow rate of the solvent. Of course, all that one will be done by using pumping system. Volume control, pressure control, all those will be done by using pumping system, which we have in the instrument. What are hydrogels? Now I am coming to hydrogels. I already explained about aerogels. Hydrogels are three-dimensional cross-linked polymer networks, highly hydrophilic and capable of absorbing large amounts of water. Capable of absorbing. I think you know the concept of absorption. Adsorption. AD. Don't get confused. Absorption. So absorption is a bulk phenomenon. This is bulk phenomenon. Adsorption is a surface phenomenon. Absorption is bulk phenomenon, adsorption is surface phenomenon. Okay. So here in this case, capable of absorbing means taking inside bulk of the material, absorbing large amounts of water, form swollen porous beads when hydrated, swollen, and those are very soft. Okay. Examples: common hydrogel materials are dextran based gels. Example: the name of the hydrogel is dextran based gels. Example: Saphadex. Okay. When you read the column details, you usually see these terminals: Saphadex, Sapharose. Okay. So all these terminologies you can see on the label of the column. Okay. Agarose based gels, Sapharose. Polyacrylamide based gels. Like this, these are the common hydrogel materials which have these properties. Role of these hydrogels in GPC and GFC. The solid hydrogels beads contain well-defined pores. Pore size is controlled by degree of cross-linking. Act as molecular sieve, allowing separation based purely on the size, not on other interactions. Size, when we are saying size, it is nothing but hydrodynamic volume. So molecule along with the solvation sphere around it. That we can say net molecular size along with the solvation sphere. Now detectors. I am coming to detectors in gel filtration process. As I have already told you, in any chemical instrumentation, whether it is atomic absorption, atomic emission, atomic fluorescence, infrared spectroscopy, UV visible spectroscopy, any chemical instrument, detector works on the same principle, measuring a particular property and converting that property into electrical signal. That is the basic principle, general. But different detectors have different ways of detection. Now let me explain to you. Detector monitor the concentration of analyte as they emit from the column. For example, if you see here, if there is a chromatographic beaker, this is elution volume and this is detector signal. I am writing detector signal because detector signal is different for different detectors. Okay. For example, if you are using this detector, refractive index, the detector signal will be RI, refractive index. If you are using UV visible detector, the detector signal will be absorbance. Okay. If this is a evaporative light scattering detector, that means scatter radiation intensity. So like this we have different detector signal. That's why I wrote DS. DS means detector signal. This is elution volume or elution time. Okay. Now tell me, I have two peaks here. One is for A, other one is for B. I am asking you a question now. Which one is having more concentration? Tell me. You don't worry, I will cut that part in the during editing, no problem. You can tell. You feel that there is nothing happening here. I am teaching you. It will be recording. It will take its work done. But later on, I will cut the unnecessary parts during editing. Right? Tell me. I am asking you a question. Which one is having more concentration, A or B? B. Okay, your answer is right. B is having more concentration. Now justify your answer.
Because it has detected signal which is higher than A.
Okay. When you are saying detect the signal higher, it is both in terms of breadth and height. Breadth and height. That means it is a matter of peak area. Area under the peak. Area under the peak. Okay? Area A under the peak is directly proportional to concentration. Don't get confused here. In UV visible absorption spectrometer, we are writing also similar expression. In UV, in other course. So here this is area. Area under the peak. Area under the peak, A is directly proportional to concentration. That is the quantitative principle. Okay? So detectors monitor the concentration of analyte. Concentration of analyte means it is quantitative analysis as they limit from the column. Because the separation is based on the molecular size rather than chemical interactions, detector choice depends on the physical and chemical properties of the analyte rather than retention mechanisms. So we have options for detectors. We have different options, and detector selection depends on the physical and chemical properties of the analyte, not depending on retention mechanism. Because retention mechanism mainly depends only on size of the molecules. That's it. Because there are no any other interactions such as electrostatic interactions, van der Waals interactions, adsorption, ion exchange, affinity. There is nothing, no any other interaction except the main property is size of the molecules. Commonly used detectors include refractive index detector, which we usually say RI. Use this detector. RI detector is also called as universal detector. Universal. Why? This refractive index can identify and detect any kind of mixture. Because every compound is having a particular refractive index, and this refractive index also different for different compounds. Okay, so we are continuously detecting refractive index. Now, for example, first solvent is flowing. Solvent will have very little refractive index. Now a particular compound entered. Now refractive index increases. Okay, that compound detected. Now again there is a gap, and that gap will be like a baseline, and then another compound coming out. So that's how it will detect. It is universal detector for detecting any kind of mixtures. UV visible detector. This will measure absorbance. Evaporative light scattering detector. In this case, we will convert the column stream into aerosol. Aerosol means the small particles. Okay, and then light, we are focusing the laser beam on them, and the laser beam will be scattered. Okay, evaporative, here the evaporative means converting the liquid into aerosol. Okay, and then making a laser beam to scatter on the droplets, and that scatter rays is the one what we are detecting. We are generating chromatography. Light scattering detectors. It is also similar. It will also work on the similar phenomenon, light scattering phenomenon. Each detector provides different types of information. Multiple detectors may also be used simultaneously. We can use also two detectors at a time. It is possible. We can use two detectors at a time because during the detection process, it will not destroy the compound. Okay. The separated compound will not be destroyed during detection process. In that way, you can use also multiple detectors. It is possible. Okay. When you are using multiple detectors, your accuracy of the output will be increasing. But when we are having two detectors in the instrument, cost will be more cost. Now, refractive index detector is the most widely used detector in GFC, especially for polymers. Key features: measures changes in the refractive index between eluent and pure mobile phase, responds to almost all non-volatile solutes, considered as a universal detector. Typical applications: synthetic polymers, oligomers, neutral organic molecules can be separated efficiently and detected. Advantages: suitable for polymers lacking chromophores, simple operation, broad applicability. Limitations: low sensitivity. Usually, if something is universal, the sensitivity will be low. Sensitivity and selectivity. I am talking about two things: sensitivity and selectivity. If there is no selectivity, that means low selectivity. Low selectivity. That means it is having wide applicability. Wide applicability. If the applicability is wide, sensitivity will be low. Sensitivity will be low. For example, if the detector is selective detector, it can applicable to only certain type of molecules. Detection of certain types of molecules. That means selective detector. If the detector is selective, then it will have high sensitivity. High sensitivity. Did you get the point? So low sensitivity, highly sensitive to temperature and flow fluctuations. That's why you need to have two streams. Only mobile phase stream, column stream. So that we will get difference. We will get difference between mobile phase stream and column stream, which are having same conditions. Not compatible with gradient elution. There is a certain kind of elution called as gradient elution. Do you have any idea about gradient elution? Actually, there are two types of elutions. Isocratic elution. Gradient elution. There are two types of elution. Isocratic elution means from the starting up to ending of your run, chromatography run, the composition of the mobile phase remains same. Okay? That means same mobile phase composition throughout. Same mobile phase composition throughout the experiment. Gradient elution means mobile phase composition keep on changing. with respect to time. With respect to time. So here with respect to time, as the time progresses, mobile composition will be same. For example, let us consider 50% methanol, 50% methanol, 50% water. This is the mobile phase composition. Let us consider 50% methanol, 50% water. From the beginning until the end, it will be same. 50% methanol, 50% water. Mobile phase composition remain constant. Now I am coming to gradient emission. Actually, gradient emission is a good facility. It is one of the facilities available with the instrument. Okay, and this is very good. In GC it is temperature. It is advantage for us. In GC, temperature is advantage for us. It is a great facility available for us in GC. In HPLC, this is the gradient emission. In gradient emission, what we will do? For example, first we know that water is highly polar compared to methanol. Okay, you can use high polar to low polar to high polar. You can change. So in gradient emission, your facility is to change the polarity continuously. First minute, let us consider 100% water, 0% methanol. 100% water, 0% methanol. First minute. Second minute, 90% water, 10% methanol. Third minute, 80-20. Fourth minute, 70-30. Fifth minute, 60-40. That means methanol is increasing, water is decreasing. Water started from 100, now volume of water is decreasing in the mixed solvent. So after some time, after maybe 10 minutes or 11 minutes, it will come to 0% water, 100% methanol. So you started with 100% water and you end up with 100% methanol. With respect to time, you are keeping on changing the composition of the mobile phase. Is it clear? That is called as gradient evolution. If it is clear about that one, this is not compatible with gradient evolution. That means we are losing a great facility. If you are using refractive index detector, you cannot use gradient evolution technique. Now you may have the doubt, why? Because solvent composition is continuously changing. For the solvent itself, refractive index will change. Not for the solute. Are you getting it? So we want a refractive index peak, then the solute will come out. But we don't want refractive index peak for solvent alone, mobile phase alone. Okay. So if you use gradient evolution for mobile phase itself, you will find peaks for mobile phase itself. That's why you should not use gradient evolution if you are using RI detector. RI detector means refractive index detector. Now we are coming to the next detector, UV visible. It will measure the absorption of UV or visible light by emitting compounds. It is like similar to attaching UV visible spectrometer. Attaching UV visible spectrometer to the end of the column. End of the column. We know what UV visible spectrometer will do. UV visible spectrophotometer will measure the concentrations. I think you have idea. It will measure the concentration based on what? Absorbance. Based on the absorbance. So in this case, the absorbance is directly proportional to concentration. The absorbance is directly proportional to concentration. Key features. It requires analytes to contain UV absorbing chromophores, operates at fixed or variable wavelengths. And advantages are typical applications. When it comes to typical applications, aromatic polymers, organic molecules with pi systems, functionalized polymers. Because when you are having functionalized polymers or pi system, they are strong absorbers. Strong, they absorb the radiation strongly. Okay? Because they absorb the radiation strongly, for those molecules which absorb strongly, we can use UV visible detector. Advantage: higher sensitivity than refractive index, because this is not applicable for all the compounds. If the compound is not absorbing, it can't detect. So higher sensitivity than refractive index. Good signal stability. Suitable for low concentration samples. Limitations: not universal. It cannot be applicable to all the compounds. Ineffective for polymers lacking aromatic or conjugated groups, because absorbance of the molecules. Which absorbance? UV visible light absorbance. UV visible light absorbance by the molecule depends on the availability of conjugation system in the compound. Conjugation or chromophores. Those are also called as chromophores. Double bond, triple bond, carbonyl group, amino group. Such groups must be there in order to absorb UV visible light strongly. Okay? Refractive index hardly completed. Now you have an activity. You need to do this one. This is activity for you. Explain the key features, working mechanisms, applications, advantages and limitations of light scattering detector or multi-angle light scattering detector. Multi-angle light scattering detector, that means MALS, as applied in gel filtration chromatography. Write down or take the photo. This is activity for you. Right? Taken? Key volumes and elution order in gel filtration. Key volume in gel filtration chromatography. So in this slide I showed you before. Wide volume V0, internal pore volume Vi, total column volume V0 plus Vi, the sum of these two. Elution volume Ve. Elution volume, that is the volume which is coming out from the column. Okay? Distribution coefficient KAV. So these are the key volume parameters. Elution order in GFC, I already told you about this. Excluded molecule is very large. Elute first, that is wide volume. Wide volume V0. Wide volume V0. Partially included molecules, intermediate elution. Fully included molecules. See, excluded. That's why I already told you. SEC, size exclusion chromatography. That exclusion came from this. Okay? From this, we have the term SEC. Size exclusion chromatography. Excluded from entering inside the pores. Excluded from entering inside the pores. Okay? So with respect to this one, we are saying this technique as SEC. With respect to this one, the smaller molecules will permeate inside. Permeate. Permeate means they will penetrate inside. We can say this one as GPC. Gel permeation. Gel permeation. Chromatography. Permeate. Permeate means they will penetrate inside the pores. GPC. Overall, it is GFC. Overall, gel filtration chromatography. Okay. So the very large molecules are excluded from entering inside the pores. They elute first, and the volume at which they are coming out are called as wide volume V0. Partially included molecules, intermediate dilution. Fully included, permeated. Fully included or fully permeated molecules which are small, elute last, and the total volume will be VT. When the smallest is eluting from the column, the total volume will be VT. Okay? Understanding the KAV in GFC. KAV means it is distribution constant. Distribution constant. The distribution constant KAV is a dimensionless parameter. Dimensionless parameter, there are no units and dimensions. Okay? Dimensionless parameter that quantitatively describes the extent to which a molecule can access the pores. Molecules can access the pore volume of the stationary phase in GFC. Distribution constant. Simply, I already explained about this. Oh, this is already 11 o'clock. Time is running very fast. So the distribution coefficient or distribution constant quantitatively describe the extent to which molecules can access the pore volume of the stationary phase. That means to what extent molecules are entering inside the pores of the stationary phase. Okay? If they are entering inside the pores, that means distribution constant will be high. Okay? If they are not entering inside, distribution constant will be low. Okay? Different molecules we have different distributions. Different distributions based on size. Based on the size. Because distributions are different, distribution constants are different. Because distribution constants are different, the migration rates are different. Because migration rates are different, the separation is good and efficient. So, is it clear? Right. It relates elution behavior of Li to the characteristic volumes of the column and is defined like this. KAV is equal to VE minus V0, VE minus VT minus V0. This is calculation of distribution constant. VE elution volume minus wide volume. Elution volume minus wide volume divided by total volume minus wide volume. This will give us KAV. Physical meaning of KAV. KAV represents the fraction of pore volume accessible to a given molecule. It reflects the hydrodynamic size, not molecular weight alone, of the analyte in solution. The value of KAV is independent of, that means distribution constant value, independent of flow rate, column length, provided ideal GFC conditions are meeting. Okay. If we maintain ideal gel filtration chromatographic conditions, the KAV is independent of flow rate, column length, and it provides the value of distribution constant. But you need to maintain proper conditions. Proper conditions means flow rate must be average flow rate, not too much, not too slow. Column packing must be uniform. You need to maintain uniform particle size, okay, and selection of the column. If you maintain all these things properly, KAV distribution constant independent of flow rate and column length. Now I am coming to implications of different KAV values. Now I already told you KAV is equal to 0. KAV 0. That means, simply speaking, I am writing an expression here. You keep this expression in your mind. I already wrote before. A molecule have you seen this expression? KAV distribution constant is equal to concentration of A in stationary phase divided by concentration of A in mobile phase. Now let us consider molecules never enter inside the stationary phase. Okay? Let us consider the molecule size is very big compared to the pore size. That means no molecule entering from that particular component. No molecule enters inside the pore. That means this will become 0. When the numerator becomes 0, it will be 0. Total KAV is equal to 0. For bigger molecules, for large molecules, KAV is equal to 0. So as the size is decreasing, now molecules start entering little bit to the pores. When they start entering little bit to the pores, that means the concentration of this one is started increasing. That means it will have some value. Definitely, this will be more than this. This will be more than this. Okay? If this is more than this one, means the value will be between 0 and 1. 0 and 1. That will show you here. KAV is equal to approximately equal to 0. Totally excluded molecules larger than pore size of the gel cannot enter the pores and travel only through the interstitial spaces. Elute at or very close to the void volume V0. Okay? Totally excluded molecules. What are the implications? No side-by-side separation among such molecules, useful for estimating void volume or removing very large species. That's it. For example, if you have two components which are having very large molecular size, and both of them are not entering the pores, that means both of them will come at once. That means two components not separated. That's why I told you, in order to separate a mixture, there must be a matching of what? Molecular size and the pore sizes of the stationary phase. Okay? Now, if KAV is equal to between 0 and 1, that means KAV greater than 0, less than 1, partially included molecules. Molecules partially penetrate the pores. VE increases elution volume increases as molecular size decreases. Defines the effective separation range of the column. fractionation of the column. Implication: optimal region for molecular weight determination. This is the optimal region for molecular weight determination. Now in the application, we have an application for molecular weight determination. I will show you. Okay. Linear relationship between this one and this one. This is very important. It is like a calibration curve. It is like a calibration curve. Logarithm of molecular weight on the y-axis, V elution volume on the x-axis will give us a curve like calibration curve. And from that we can determine molecular weight. Best relation between species of different sizes if K is between 0 and 1. That means we need to maintain all the conditions in such a way that the KAV is between 0 and 1. Okay? KAV 0 also not good, KAV 1 also not good. Okay? If KAV is 0, that means all the large molecules will not get separated. All the large molecules which are having size more than the 4 sizes, they will not get separated. If it is equal to 1, K is equal to 1, that means some molecules will remain in the column without coming out. Particularly smaller molecules will stay in the column without coming out. That means you will be missing some of the components in the column. Okay? You can see here. KAV is equal to 1. Fully included molecules. Molecules are small enough to access almost all the pore volume. LU is the total column volume. Sometimes they may stay inside. Okay? Implications: poor resolution between very small molecules. The species are often not the primary target in GFC analysis. Practical interpretation for column selection: good separation. Analyze should have KAV values between 0.2 and 0.8. This is the best KAV range. Distribution constant range between 0.2 and 0.8 is the ideal range of distribution constants. If you have the distribution constants for every component, if you have distribution constant range between 0.2 and 0.8, you will get very good chromatogram. You will be able to separate all the components without missing. Even very small molecules also you can separate. Bigger molecules also you can separate. Poor separation. KAV is equal to 0, KAV is equal to 1. In both the cases, poor separation. Choosing a gel with the appropriate pore size shifts analyte into optimal KAV range must be done. Okay? Now, logarithm of molecular weight versus elution volume relationship. This relationship. Logarithm of molecular weight. Logarithm of molecular weight versus elution volume. As we know very well, on the x-axis it is elution volume, on the y-axis molecular weight. If you take the logarithmic function, logarithm of molecular weight. Let me show you here. This is the graph. You can see here. Have a look here. This is the graph. Elution volume in milliliters. Logarithm of molecular weight on the y-axis, and you can see, have a look here. This is the, because this is logarithmic function, we are getting a graph like this. And in this graph, it is a linear graph. And we know for linear, we have y is equal to mx plus c, where y is the y coordinate, x is the x coordinate. X coordinate means this one, y coordinate means this one, and m is a slope. and C is intercept. And intercept, if you extrapolate this one, wherever it is touching, that is intercept. That is intercept. Y is equal to mx plus c. Okay? Now by using this one, you will be able to determine molecular weight of a particular fraction. You will be able to determine molecular weight of a particular fraction. It is possible. In GFC, molecules are separated according to hydrodynamic volumes, which correlates strongly with molecular weight for molecules of similar shape and chemistry. Within the fractionation range of a gel, there is approximately linear relationship between logarithm of molecular weight and elution volume. This is like this. Logarithm of, that means this is y coordinate. This is y coordinate is equal to mx plus c. Okay? In the base of y coordinate is logarithm of molecular weight, x coordinate is elution volume, and a is slope, b is intercept. MW is molecular weight, b is elution volume, a and b are column calibration parameters. Simply we can say a is slope, b is intercept. This linearity arises because larger molecules are excluded from pores and elute area low VE. Smaller molecules penetrate more to the pores and elute later high VE. The pore accessibility changes progressively with molecular size. That's why we are having this relationship between logarithm of molecular weight and VE, elution volume. So to construct a calibration curve, you need to inject a series of standards with known molecular weights, record the elution volumes, VE, plot logarithm of molecular weight on the y-axis and V on the x-axis like this. Fit a straight line in the linear region. Okay? This is also called linear fit. Linear fit. You need to define these ones with a linear fit. Negative slope. As the elution volume increases, molecular weight decreases. As the elution volume increases, molecular weight decreases. Okay? Molecular weight decreases means smaller molecules. Smaller molecules. So here bigger molecules, here smaller molecules. As the elution volume increases, molecular size decreases, molecular weight decreases. So elution volume increases. As elution volume increases, molecular weight decreases. That's why we have negative slope. Linear middle range corresponds to molecules that are partially included in the pores. That means here. Non-linear ends. Sometimes there will be non-linear ends. For this curve, non-linear ends means there may be some deviation like this. There may be some deviation like this. There may be some deviations like this. Non-linear ends. Left side near V0. Very large molecules excluded. Leads to non-linear. Right side near VT. Very small molecules fully excluded. Simply we can say if this is for KAV is equal to 0. This is KAV is equal to 1. Okay? If KAV is equal to 0, non-linear. If KAV is equal to 1, non-linear. If it is between 0.2 and 0.8, linear. It is linear. Practical implications. Only analyte eluting within the linear range can have their molecular weight determined accurately using this method. Only analytes eluting within the linear range can have their molecular weight determined accurately using this method. That means this method is useful even to determine the molecular weights of the compounds present in the mixture. In addition to qualitative identification, quantitative analysis, this application is also useful for the determination of molecular weight of the compounds present in the mixture. Molecular weights of the compounds present in the mixture by using this method. Okay. You can see here example 1, estimating molecular weight of unknowns. Okay. So we have a lot of things to discuss. Okay. From this example 1 onwards, maybe I will teach in the next class. I am stopping here forcefully. Why forcefully? Because